It's time to start our event. A very warm welcome to everyone. I am Jasmeet, your host for this event. First of all, I would like to thank our speaker, Professor Vipul Rastogi, sir, our department convener, Dr. Nimi Singh, our respected professors, and all our guests for joining us today for the fourth webinar of the Perennial Series, an excursion through the wonderful world of fiber optics, organized by the Spark Society. Let me brief you with the guidelines to follow throughout the webinar. Please keep your mics off. If you have any questions or queries, feel free to put them in the chat box. You will be called out by your name to ask your question in the interactive session, which will be done at the end of the lecture. That is when you can unmute your mic and ask your question. This lecture is being live streamed on YouTube, so if you want to invite any of your friends to attend, you may provide them with the link that is in the chat box. All of these guidelines will also be posted in the chat box. Now, I would like to hand over the spotlight to our professor, Dr. Savinder Kaur.
Thank you, Jasmeet. Uh, I would actually like to welcome Professor Rastogi on behalf of the Spark Society. So it's a pleasure to have him here. His expertise lies in fiber optics, and you will be happy to know that he is developing MTech photonics at IIT Roorkee, which will very soon be a full-fledged department. And he has been awarded a Ram Kumar Prize for outstanding teaching and research. And I think you all will feel from the deliverance in his talk today. He's also the vice president of the Indian Association of Physics Teachers, and he has many, many more honors and awards to his credit, which I will not go into. So I would welcome him, and I think let's go through this excursion on fiber optics. It's a different world altogether that he's going to present today. So welcome, Professor Rastogi, and thank you, Jasmeet.
Now, I would like to ask Garvit Kumar, President of the Sparks, to introduce the event and the speaker.
Good evening, ladies and gentlemen. The internet has enabled us to connect with our friends and family sitting miles away from us. We can now watch a sports event happening oceans across using our mobile phones. Sharing of information has never been faster. Even the conduction of this webinar has been made so quick and convenient with the help of high-speed internet. This can be attributed to fiber optics. With this remark, I welcome you all to Professor Vipul Rastogi's webinar on an excursion through the wonderful world of fiber optics, organized by Sparks, the Physics Society of SGTB Khalsa College. Professor Vipul Rastogi did his PhD from IIT Delhi in 1998 and postdoctorate in Université de Nice, Sofia Antipolis, France from 1998 to 1999. After working during 2003 in the City University of Hong Kong, he joined the Department of Physics at the Indian Institute of Technology, Roorkee, in November 2003. His current research interests are optical fiber designs for high-power lasers and high data rate optical communication, orbital angular momentum modes in fiber, erbium-doped fiber amplifier, optical fiber sensors, and optoelectronic devices. He has over 200 research papers in refereed journals and conferences, has 4 patents, and developed codes of 2 commercial software. He is a fellow of the Optical Society of India, senior member of Optica, member of IEEE Photonics Society, life member of Indian Laser Association, life member of Indian Association of Physics Teachers, and life member of Indian Physics Association. He also mentors the IIT Roorkee student chapter of Optical Society of America. I now invite Professor Vipul Rastogi to begin with the session.
Okay, thank you very much. The entire team of Spark Society, Dr. Savinder Kaur, Dr. Nimmi, Jasmeet, and Garvit for nice introduction, generous introduction. Thank you so much. So as you can see that today I am able to talk to you. Today I am able to present you this talk through online mode and that is because of fiber optics. As Garvit has mentioned in the abstract of the talk itself, that fiber optics has really made our world very small and wonderful, right? So I will begin with this. So let me share my presentation. Uh, Let me see. Are you able to see my screen?
Yes, sir. Yes, sir. Yes, sir.
All right. So let me just choose laser pointer. Fine. So this is an excursion through the wonderful world of fiber optics, and why I call it wonderful, because it's really fiber optics which has made this world wonderful, in my opinion, because we are able to talk to each other so quickly. Even though my friends or family, they are sitting in America, Canada, or London, wherever they are just a call away, and not only voice call but video call. Okay, as if I am talking to them in person. So, and this has become possible because of fiber optics. So I would say that the fiber optics has really made our world wonderful, and we are going uh, through this wonderful world. We are going to take a small excursion, maybe 1 hour excursion through this. So, what is this optical fiber, first of all? So, which has made tremendous contributions the way we communicate today, okay? And in other things also. If you look at the fiber, it is a hair thin glass or plastic structure. Usually, when I will refer to optical fiber, I will refer to optical fiber which is used in telecommunication, and particularly in long distance or long haul telecommunication. So the fiber which is used in communication is hair thin. How thin it is? Well, you just get a feel of your hair. Your hair is about 62 micron across, and optical fiber is 125 micron across. So it's so thin, right? And in such a tiny structure, tiny in the sense in transverse dimensions, length can be kilometers. So in such small transverse dimensions, you have even very, very small core which has high refractive index. For telecom fiber, it is just 10 micrometer across. And then you have a cladding which is having slightly lower refractive index, and it is 125 micrometer across. So it is such a small transverse dimensions, right? And through this, our data, video data, voice data, pictures, email, books, encyclopedia, all of them can be transmitted with very, very large speeds. Okay, so this is such a wonderful thing. All right. So this we know, all of us are aware of, that the fiber is used for telecommunication, but when the fiber was initially developed, it was not used in telecommunication. So let us look at how fiber is affecting, or fiber is making our lives much easier, where the optical fiber is contributing. So we have use of fiber. The very first use of fiber was in medicine, basically endoscopy, where with the help of optical fiber, you can image internal organs of a human body. And it is so wonderful thing, because you see it is a flexible structure, so you can slip it in through mouth of a person, and you can put some, camera there, some light there, and then from there you can image the internal organs of human body. So this was the very first use of optical fiber, that is in endoscopy. Now it has been extended to not only viewing these internal organs, but also doing surgery using optical fibers and lasers. So even in so optical fiber has made tremendous contribution, is making tremendous contribution in the field of medicine. Second example that I would like to give you is smart structures. What are these smart structures? So you have a flyover, for example, okay, and in this flyover, there is a lot of traffic, and there, because this is civil structure, so there might be some crack developing at some place, okay. And if you install optical fiber structures, optical fiber sensors, then you can do 24 by 7 monitoring of these kind of structures in real time. And while monitoring this, if there is some unusual crack is developing, unusual thing is going on the bridge or any other civil structure, then it will make an alert that something is happening at this point in the bridge, and then you can take corrective measures, and you can prevent losses of life and loss of structures. Okay, so such kind of structures where you install fiber optic sensors, they are known as smart structures. Third example is cold lighting. What is this cold lighting? If you look at museums, in museums where you have very, very expensive artworks which are kept there, and you need to illuminate them, if you use normal lamp, then normal lamp not only produces light but also a lot of heat, and that heat is not good for those artworks. So what you do, basically, you keep the lamp outside, and then take only the light from that lamp through optical fibers into the museum, and not the heat. So in this way you can illuminate the artwork, illuminate the museums, and while at the same time preventing degradation of these artworks by heat produced by the lamp. So this is known as cold lighting. This is the example of Ajanta caves in Aurangabad, taken by myself. All right. Other uses of optical fibers which you might not realize are, one is personal use, right? What you can do, you can weave fiber with the fabric and then illuminate it with LED light, which, and light can change color. You can have light changing multicolor LEDs, and so these fibers are illuminated. So you can have the fabric which is lighted up, and that can also change color. So you can improve your ambience. Okay, you can sit on light, you can dine on light, you can sleep on light, whatever you want to do. Okay, even some people do light therapy using these things. Some other uses are in industry. So let me tell you that optical fiber can not only be used in like an endoscope, like a sensor, like a light pipe for cold lighting or to improve your ambience, but also in industry, how you can make lasers out of optical fiber. And fiber lasers are very popular these days. And let me tell you that with optical fibers, you can make very, very, very high power lasers, which and very compact also. And with the help of these lasers, you can do industrial applications. You can have like welding two metals, cutting, drilling holes, cutting metals, okay, very thick sheet of metals. All these things you can do with the help of fiber lasers. And the advantage with this is that one thing is that these lasers are very compact. You can just use them as backpack. And second thing is that the distance between the object and laser head can be large. Okay, so you can work at some distance from the object. So that is also very useful. Another use is that no, a beautiful stone, the wonderful stone is diamond, right? And from this natural piece of just coal, kind of coal, it is carbon basically. You can transform it into such a beautiful stone which is sparkling with the help of fiber lasers. Okay, in Surat, in India, there are lots and lots of fiber lasers which people use to cut, polish, and give shape to these stones and make diamonds, right? But as you know that we started with this, the most important, interesting, and useful application of optical fiber is in telecommunication. Okay? Today, all of us are connected across the oceans through various social media, various email services, internet. Okay? All these things just because of optical fiber. Okay? You will say that okay, we are using all these things, and I don't see any optical fiber anywhere. I talk to my friend, I'm sitting in Mumbai and I'm talking to my friend in Delhi on mobile phone. Where is optical fiber? I don't see any optical fiber there. So this is true that the fiber is not coming to mobile, but it is coming to a cell tower near your mobile. How it is working? In fact, this is the combination of mobile and optical fiber which is keeping us connected across the oceans, across the cities, across the countries. Okay? How does it work actually? So when you are in your college and you call your friend who is also in the college, then these two mobile phones communicate to each other using a local cell tower which is in the vicinity of your college, right? But if you want to talk to somebody who is far from your college in Delhi, then this cell tower communicates with another cell tower through a microwave link, and this microwave link has a data rate of about 100 mbps over a few kilometers. Okay, what is this data rate? You will get to understand a little later. It is nothing but the data is binary data in the form of zeros and ones, and each zero and one is called a bit. So in 1 second you are sending 100 into 10 to the power 6 bits. Okay, so 100 megabits in 1 second you are sending. Okay, so this is the link. This is the capacity of this link. You cannot send data more than this rate using a microwave link, right? But if you now want to talk to somebody who is in Mumbai, then your data goes from this cell tower to this cell tower, and now from Delhi to Mumbai, it is not a microwave link because the distance is very large. This microwave link can give you this kind of data rate only over a few kilometers, okay, a couple of kilometers. But if you want to talk to somebody in Mumbai, then this data goes from a cell tower in Delhi to a cell tower in Mumbai through optical fiber link. Okay? This optical fiber link has data rate of 10 to 100 Gbps. Okay, so you can see at least 10 to the power 3 times data rate which a microwave link can offer. Okay. You may also download something from a website which is hosted in New York. Okay. So how the data comes from that website, that computer which is placed in New York to your mobile phone. Okay. And this is through submarine fiber optic cable. So what I mean to say is that we are connected globally with the help of optical fiber network, and this optical fiber network, these optical fibers, there are millions of kilometers of optical fiber which is laid on seabed, connecting all of us. You see these lines are nothing but optical fibers which are laid on seabed, right? These are submarine cables. I have talked about this. I've used this term fiber optics quite some time, and you will be amazed to know that this term fiber optics was coined by one Indian whose name was Narinder Singh Kapani, who died just a few months ago. Okay, he was born in Moga, Punjab, and educated in England. His was the first PhD thesis on fiber optics from University of London in 1955. So since he coined this word, this term fiber optics, so he is often referred to as father of fiber optics. Okay, Narinder Singh Kapani. Now, so I have talked about, okay, uh, if I use optical fibers, for high data rate communication, we use optical fibers. Okay, and we also know that optical fibers, they carry light. Okay, the question is that why microwave link or copper wire link cannot offer you such a high data rate which optical fiber is able to do. Okay, let us try to understand that. And since the communication through optical fiber takes place through laser light, then the first question that comes to our mind is why light for telecommunication after all? Okay, why not only microwaves or radio waves? Okay, as we know that the telecommunication that takes place over long distances is through carrier waves. Okay, so this is known as carrier wave communication. We have studied this in our school or maybe in our college also. Okay, so this is the most reliable, economic, fastest way of communication between 2 points, and this is through electromagnetic waves. So what is a typical block diagram of this communication channel, communication system rather? You have a source, okay, source, data source, your voice source, video source, picture, whatever it is. So from source, the information goes through communication channel and then it is received at the other end through a receiver. And this communication channel can be atmosphere for radio broadcast, electric lines for telephone, wireless network for mobile phone, and optical fiber for optical fiber communication. Right? So these are the examples of various communication channels. Fine. Now, what should be the properties of this communication channel? The very first thing is that since we want to send data over a large distance, so it should introduce less loss and less distortion to the signal. Okay, first thing. Second thing is we want to have reliable communication system. So for reliable communication system, I would say distortion should be minimum. So when I am talking to you, you should hear my voice very clearly, okay, without any disturbance. If you're seeing my video, my presentation, there should not be any disturbance there. You should be able to see it very clearly. Okay, so the channel should introduce minimal distortion. Second thing is noise added by the channel should also be very little. So that my signal comes out of that noise level very clearly. It should not be embedded in noise level, and you should be able to get that data very precisely and clearly. Okay. Now, since it is through electromagnetic waves, and our data is usually in the form of electric signal, whether it is a voice signal by telephone. So the voice signal gets converted into electric signal using a transducer, which is called mic. Then it is computer data. So computer data is again, it is in the form of zeros and ones, electric pulses. Video data again in the form of zeros and ones, electric signal. So the electric signal produced by these sources, they are not always directly suitable for transmission through the channel. You cannot just send these signals directly through communication channel. What you do is basically you write these signals over a high frequency electromagnetic waves. Okay, and this electromagnetic wave can be radio wave, microwave, or light wave. Okay, depending upon its frequency. Okay, so these are known as carrier waves. So your signal writes on this carrier. That is why it is called carrier. Okay, now this signal modulates this carrier, and this modulated EM waves carries the information, and that's what is known as carrier wave communication. Okay. So I give you a very simple example, although this is not used in communication these days. This is amplitude modulation, but it is easier to understand with the help of this. So you have a carrier wave, which is a high frequency wave, okay, has certain frequency, right? And this is a voice signal, which has a large number of frequencies, and that is why its waveform is like this, okay? Carrier wave has a frequency, let us say nu c, and the voice signal has maximum frequency nu m. It has a range of frequencies, and if I pick up what is the maximum frequency there, let us say it is nu m. When this voice signal modulates the carrier, then this is the modulated carrier which you see here. Now this modulated carrier does not have a single frequency, but it has a range of frequencies which goes from nu c minus nu m to nu c plus nu m. We know all this thing. Okay, which is very simple thing. All right. So this is now the modulated carrier which we send across. Fine. Let us understand it now with the help of an example. If I want to transmit a speech signal, for a speech signal to be intelligible, it is sufficient to send signal content up to a frequency of 4000 hertz. You will say voice signal has frequency from 20 hertz to 20 kilohertz. Okay, why to limit it only up to 4000 hertz? Well, you see, if I'm just making a telephone conversation, if I'm making a voice call, then if I cap this frequency up to 4000 and I remove all the frequency content above 4000, then also my information, my voice, what I am talking can reach you without any problem. Only thing is that there would be a different texture of my voice. The texture of my voice will change because I've removed high frequency content there. So the shrill in my voice would be missing, but whatever I am talking would be you would be able to completely understand this. Okay. So electric signal produced by the mic can be restricted to a maximum frequency of 4000 hertz. Of course, if you're sending, high fidelity music, then you would not like to cap it. You will like to send all the frequencies. Okay. So electric signal from the noise, the maximum frequency is 4000 hertz. Carrier wave frequency, let us say I'm using radio wave, which is 1 megahertz. Okay. Radio waves, you must have, these days nobody listen to radios. Okay. Perhaps FM radio you listen to, but AM radio nobody listens to. Okay. In AM radio, if you look, then the typical carrier frequency is 1 megahertz. Okay. And so if you look at the frequency content of modulated wave, then it goes from nu c minus m to nu c plus nu m, which means 996,000 to 1,004,000 hertz. Okay. So this is your modulated wave, frequency content of this modulated wave. What does it mean? That, let us understand this. Now, this band nu c minus nu m, this entire band can be divided into two bands, nu c minus nu m to nu c and nu c to nu c plus nu m. And both these bands contain the same information. This one is known as lower sideband, this one is known as upper sideband. And we can use any of them for sending our information because they contain the same information. Right? So let me choose the upper sideband, which means that 1 million to 1,004,000 hertz. So I can reserve this band. I can reserve the band of this frequency for one voice communication, right? Or one voice channel. Okay. If you look at your, even FM radio, right? What you do, you tune it over a frequency range. Okay. 102.6 megahertz is rainbow, 100.5 Dehradun, or 98.6 another. Okay, these megahertz. So these are different bands, and you can see that these frequencies which you are tuning, they lie in a certain range. Okay, so that is the bandwidth available to you. Okay, similarly, if it is AM radio, then if you have tuned the radio from one end to another end, so there is a range of frequency. Okay. For example, Vivid Bharati Delhi, 1368 kilohertz, okay, 1.368 megahertz. So that is the frequency where you tune it. Okay. So near that frequency, a band of this frequency, a band of 4000 hertz is reserved for example, Vivid Bharati Delhi. Okay. So around that frequency, you will receive Vivid Bharati and you will get information. So the band of 4000 hertz is reserved for one speech signal or one voice channel. Okay. Now you can have another band, another radio station near that, maybe I don't know, 1600 something kilohertz. So near that you can have another channel, another radio station. So that also you can reserve a band of 4000 hertz there. So you see, what I have a range of frequencies over which my carrier frequencies are available, and for each band, for each carrier frequency can be used as one voice channel, one radio station, and that occupies a bandwidth of 4000 hertz. So within 4000 hertz of that channel, I cannot have another channel, right? That's what it means. So now if a carrier is available to you from 1 megahertz to 3 megahertz, that is 2 megahertz bandwidth system is available to us. This is the spectrum basically. This is the spectrum available to us. When government auctions the spectrum for mobile phones, it is basically this kind of spectrum, right? So in this spectrum, in this bandwidth, the number of speech signal that can be sent simultaneously would be this 2 megahertz bandwidth, and each channel will require 4000 hertz, so about 500 channels. Okay, so 500 voice communications you can have simultaneously if you have this much bandwidth available to you. All right, this much spectrum available to you. Now, if I increase this, instead of megahertz system, megahertz carrier wave frequencies, if I have gigahertz carrier wave frequencies, gigahertz is basically microwave frequencies. Okay, so 1 gigahertz to 3 gigahertz, that is 2 gigahertz bandwidth system. Then I can have 500,000 in digital communication. What you do if you have this modulate this voice signal, then at University of Geneva in 1841. Okay, so I have taken this image from this book, Hacked City of Light. Right? So now coming to optical fibers, so people have realized that optical fibers are needed for communication, and people started working on that. And in 1951, Holger Moller Hansen, he applied for a Danish patent on fiber optic imaging, in which he proposes cladded glass or plastic fibers with a transparent low index material. So this was for imaging, sending image from one place to another place. And it could be done only over a couple of meter or only over a meter. Okay. In 1956, Curtis made first glass clad fiber, okay, by using a method which is known as rod and tube method. Don't worry about that. Okay. So, but in between, in 1955, Narinder Singh Kapani completed his doctoral thesis on fiber optics under Professor Hopkins, and he moved to University of Rochester. And he proposed this cladded fiber, and he coined this term fiber optics. And but his work was also limited to sending images from one place to another place using optical fibers, which are not longer than a couple of meters, maybe just 1 meter or so. So this kind of fiber could be used for applications like endoscopy, but not for communication, because for communication you require kilometers length of fiber. Okay, and these fibers were so lossy that even after 1 meter, the output was very, very low. Okay. Remember that this was the years were 1950s. Okay, and you had normal optical sources, no optical lamps, okay, sodium lamp, tungsten halogen lamp, all these kind of things. Laser was not there. Okay, and then in 1960 a revolution happened. Laser was born. Okay. Theodore Myman demonstrated ruby laser in Malibu on May 16, 1960. So let me tell you that May 16 is also celebrated as International Day of Light every year. Okay? UN has declared May 16 as International Day of Light because laser was invented on this day, right? So this was the ruby laser, which was invented by Theodore Myman. Let me not go into this. This is the helium neon laser, which the same year. Eli Javan, he invented this helium neon laser. Ruby laser was pulsed laser, and helium neon laser was the first steady beam laser. So continuous wave laser. Okay, no pulses. Continuously the light was coming out. Okay. So let me come back to this communication. So during 1962 to 1963, experiments showed very high loss when sending laser beams through atmosphere. So when lasers were there, so people had this renewed interest in telecommunication using laser beams. Okay, because now you have very powerful directional coherent source of light. Okay, and this was very exciting. So people even thought that we can send signals using laser beams over long distances from one building to another building. Okay. So through open atmosphere. But you see, if you do it, then of course, if it is line of sight communication, there are a lot of limitations. There is a fog which is settling in, rain. If it rains, then the signal is absorbed by water. So all those problems are there when you have line of sight communication. And if you use optical fibers, then optical fibers already showed too high loss to be used for telecommunication, even with the help of laser sources. That's what at that time people were thinking. Okay. So during that time, America was leading the work in developing lasers and optical fiber both. But lasers for other applications and optical fiber for other applications. And the Americans they virtually ignored the idea of optical fiber communication. But at that time itself, one young engineer from one Chinese engineer, Charles Kao, he was still pursuing the idea of optical communication through these hair thin fibers. Look at it. What was the state of art at that time? The state of art at that time was the optical fibers were having losses of 100 dB per kilometer. I'm sure you people are familiar with these units, dB per kilometer, which means that 1% light remains after 20-meter long fiber. So you have 20-meter long fiber, okay? You send 100 milliwatt light, okay, laser beam, okay, and at the output end, you will be left with only 1 milliwatt. 100 milliwatt is too large, okay. Let me tell you that when you send light through optical fiber for communication, it is few microwatts, okay, not milliwatts. Well, so so what Charles Cow did, Charles Cow now had optical fibers which were available at that time. He had with him the lasers. He knew what are the laser powers available, and then he had detectors, okay, which convert light into electric signal. So he knew what is the sensitivity of the detector. Okay, so all these three things he had, and he analyzed them very carefully, and he made a daring conclusion. What was the daring conclusion? He said that a fiber with 20 dB per kilometer loss can realize the dream of optical fiber communication. What is the meaning of that? Just look at it. If I convert 100 dB per kilometer into loss factor, then it comes out to be 10 to the power 100, which means that the loss factor in the fiber available at that time was 10 to the power 100. And he was proposing if you bring down this loss factor to 10 to the power 2, from 10 to the power 100 to 10 to the power 2, then the dream of optical fiber communication can be realized. You must be joking, Mr. Cow. But no, he was very serious about this. In that paper in 1966, which he wrote, he carefully analyzed everything, and he in fact proposed that you have to bring down the losses of optical fiber. The fiber available at that time were having lots of impurities. So you will have to cut down on those impurities, and then you come up with a fiber with 20 dB per kilometer loss, and then optical communication will take off. At that time, a very big company which was working in optical glasses was Corning Glasswork. Okay? We also have glass from Corning. Okay? So in 1970, this Corning Glasswork, they took this idea very seriously in 1966, and they worked very hard for 4 years, and in 4 years time they came up with a fiber which was having 16 dB per kilometer loss at 633 nanometer wavelength. And bingo, wow, eureka. And from there, optical communication took off. Within a decade, from 1970 to 1980, fiber loss could be brought down to 1 dB per kilometer. And today we have optical fibers which have losses less than 0.2 dB per kilometer. So this is the fiber which we use right now. Of course, this loss is not at this wavelength, 633 nanometer, but at 1550 nanometer wavelength. Okay? So you see the losses in optical fiber have come down from Egyptian age 10 to the power 7 dB per kilometer to now 0.2 dB per kilometer. Okay, so for his proposition analysis and daring conclusion basically which he made, so I would like to tell students that you should be no smart enough, you should be able to make these kind of daring conclusion if you have confidence. Okay, you should not shy away from putting forward your ideas, okay, even if they are daring. Okay, so Cow is widely regarded as father of optical fiber communication. Okay, and he received 2009 Nobel Prize in Physics for that. Right. Now let us understand how optical fiber guides light. So we have understood, okay, optical fibers are the structures. This is the transmission medium which can carry light over long distances without much loss along all the curves and corners. Okay, how these fibers now guide light? We have briefly looked at that this guidance may be due to total internal reflection. Okay, so let us look at optical fiber structure. So it has a core of high refractive index, and the refractive index score is usually labeled as N1. It is surrounded by a cladding of slightly lower refractive index. The refractive index is labeled as N2, and the difference between the refractive index is defined in terms of relative index difference, delta, which is defined as n1 square minus n2 square over 2n1 square. And let me tell you that optical communication grade fiber has very small difference between n1 and n2. Okay, so if you approximate it, then it can be written as n1 minus n2 over n1, that is index difference relative to core refractive index or relative to core reflect or cladding refractive index. These are known as weakly guiding fiber. And let me tell you, this delta is just 0.3%. 0.3% means 0.003. Okay, such a small difference. Okay, relative index difference. Core has finite dimensions. So the radius of the core is, let us say, a. So here you have refractive index n1. Refractive index, so sorry, the dimensions, spatial extent of cladding is in standard fiber 125 micrometer. And since this is just 5 micrometer, this is 125 micrometer. So usually what we do, we consider the cladding to be infinitely extended most of the times, okay, for telecom fiber. Okay, so this is how the refractive index profile of a fiber looks like, right? So how does it guide light? So as I've said that we can take clue from lighted fountains. So now here in the optical fiber, you have high refractive index, which is surrounded by lower refractive index. Okay. And so when a ray of light strikes the core cladding interface, then there is a total internal reflection. And then there is it comes back, then at this interface there is total internal reflection. So through successive total internal reflections, the light can be guided over kilometers of distance in an optical fiber, right? And as we can see that since this is total internal reflection, so we have to satisfy the condition of TIR, which is total internal reflection in short. And so there is only a limited cone of light which would be guided. Okay, so this red cone of light the rays in red cone of light will satisfy the condition of total internal reflection, and light would be guided in the core. While if you go beyond that, if you enter into green region, then the rays would be refracted. Okay, so this cone would be guided, but this cone would not be guided, right? And if you apply the condition of total internal reflection, then you can find out what is the maximum acceptance angle, okay, for guidance of light by this fiber. And this is given by sine I max is equal to square root of n1 square minus n2 square over n0. N0 is usually air. So we can just write it as square root of n1 square minus n2 square. So it basically depends only on the refractive index contrast between the core and the cladding. and this is known as numerical aperture of the fiber. Okay, fine. So now there is one intricacy here. We talked about ray theory here, and we know that if the dimensions with which the light is interacting are of the order of wavelength comparable to wavelength, then ray theory does not work. Okay, then what we'll have to do, we'll have to use wave theory, we'll have to use electromagnetic wave theory of light. We'll have to start with Maxwell's equations. Okay, if you look at telecom fiber, the diameter of core is 10 micrometer. The wavelength which we use is 1550 nanometer, 1.55 micrometer, which is comparable to this. So ray theory does not work. Okay. Then, then how do we understand guidance of light in an optical fiber? Now you will see how does it matter? How does it matter? How, after all, we would like to understand whether in terms of ray theory or wave theory, how light reaches from this end to that end. It is important because we send data in the form of temporal pulses. Okay, and we would like to know what will happen to these pulses when they travel through optical fiber, because that ultimately will determine how much data we can send through optical fiber. Okay, so we need to understand, if we send some intensity pattern through this optical fiber, how will it propagate through optical fiber? Okay, and so when we talk about wave theory, then we come up with the concept of modes of an optical fiber. Okay, understand it, that if you have an optical fiber, you send, for example, this laser beam, the laser beam which has this profile, which this transverse profile. Okay, you send it through optical fiber, and you want to know what is the intensity profile at this point, at this point, at this point, at this point. That is how intensity profile evolves as it propagates through optical fiber. And you would not have any answer. Okay, you cannot tell, okay, how would it evolve. Okay, okay, and I want to know how would it evolve. So how do I do it? Okay, then what happens is, actually there are certain intensity or amplitude patterns. When you send them through optical fiber, they travel through optical fiber without any change in their shapes. Their shapes are sustained. Okay, and this is a wonderful thing. Their shapes are sustained and they travel with certain velocity. So this pattern travels with certain velocity, this will with certain other velocity, this certain another velocity. Okay, and 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 these patterns which sustain their shape are known as modes of an optical fiber. You must have come across most of the time single mode fiber, multi-mode fiber. What are these fibers? What are the modes of fiber? These are the modes of the fiber, right? You'll say why it is important to know, okay, these modes of the fiber. Well, if you send a laser beam through a thick glass block of refractive index, and let us say this is 2 centimeter by 2 centimeter transverse dimensions. Okay, this block of glass, and your laser beam is just a few millimeter across. So this laser beam will go through it. It will not encounter any refractive index discontinuity across it, and it will go with velocity c by n. N is the refractive index of the material at this wavelength. Okay, fine. Now, if you bring down the dimensions of this of the order of micrometer, okay, that is, you use optical fiber. This is the transverse profile of an optical fiber. So core is 10 micrometer across. Now your beam is much larger here. So part of beam is in this N1 refractive index region. A part of that is in N2 refractive index region. So with what velocity this pattern will go? Whether it will go with C by N1 or it will go by C by N2. Okay. And the answer is it will depend upon the intensity profile. This intensity profile will go with different velocity and this will go with different velocity. But intuitively, I can say that it would be between C by N2 and C by N1, or C by N1 and C by N2. So now this profile, this intensity profile will experience the refractive index of this composite medium, neither N1 nor N2, but something in between. And that we call effective refractive index. And since this effective refractive index depends on the pattern, that is depend on the mode, so we call it effective index of the mode, and this will decide the velocity of the mode. Okay? So different modes will travel with different velocities. Now, in an optical fiber, you may have modes, okay, which confine light in the core, okay, and there might be mode which have light in the cladding, lot of light in the cladding, and the light travels through this structure in the cladding itself. Okay, so and in the cladding, this basically since there is no guidance, so light radiates out. Okay, so what we divide these modes into two categories. One is the modes which confine light in the core itself. Most of the light in the core, only certain amount of light spreads into cladding. Okay, but as you go away from the core, the light in the cladding will eventually die out. So most of the light will be in the core itself. Okay, so these are known as guided modes. Okay, and the modes which for which most of the light lies in the cladding and which radiates out, they are known as radiation modes. So these guided modes are discrete. There are only certain field patterns, certain intensity patterns which form discrete guided modes, and the radiation modes form continuum. Okay, the important thing is that these modes are orthogonal. Okay, these modes are orthogonal, they form a complete set, which means that, what does it mean? It means that if you take any arbitrary field distribution, then that arbitrary field distribution can be expressed as a superposition of discrete guided modes and continuum of radiation modes. So when you send light through optical fiber, any arbitrary field patterns, so for mathematical convenience, you can say, okay, of this intensity pattern, this much is going in this mode, this much is going in another mode, this much is another mode. Okay, and you can predict how each mode travels because each mode sustains its shape, but it travels with different velocity. So if at any point in optical fiber, for example, let me go back. For example, here, okay, you want to know what is the intensity pattern. Then what you will do, you will superpose all the modes of the fiber with accumulated phases because they are traveling with different velocities. So they will accumulate different phases when they travel certain distance. So at this point of time, you will superpose all those modes of the fiber with accumulated phases because now you know the amplitude pattern of the mode, you know how much phase has been accumulated because you know the effective index of the mode, you know the velocity of the mode. Okay, so when you superpose them, then you can get to know, okay, what would be the pattern here, what would be the pattern here, what would be the pattern here. Okay, so these are the modes. Okay, these are some modes of an optical fiber. Okay, and in an optical fiber, if you look now, we have three parameters which determine the light guidance of optical fiber. What are the parameters of optical fiber? Refractive index of the core N1, refractive index of cladding N2, and the radius of the core. These three parameters. Eventually, the refractive indices, they contribute in the form of index contrast or NA. So we have eventually only two parameters, numerical aperture and core radius. Okay. The question is that how many modes an optical fiber would support. Okay, would any optical fiber support infinite number of modes, or there are certain number of modes? There is a limit on that, and there is a limit on that. Okay, so it will depends on the parameters of optical fiber as well as the wavelength of light which we use. Okay, so if I fix the wavelength of light, let us say 1550 nanometer, and then I fix the material of the core and cladding also. So I fix the numerical aperture, and then I see, okay, if I have the core radius 20 micrometer, so these many modes are supported. Okay? You can calculate that. You can experimentally find that out also. Okay? So these many modes are supported. You can see these beautiful patterns. So these are different modes of an optical fiber. Okay? When I bring down the core radius to 15 micrometer, some of the modes are no more supported. So these two are not supported, only these modes are supported. I further bring down the core radius, only two modes are supported. I come down to 8 micron, for example, only one mode is supported. So a fiber with 20 micrometer radius is a multi-mode fiber, and with 8 micrometer radius, it is a single mode fiber for a given numerical aperture. Okay? So you have a smaller core, less number of modes. Fine. Let me now look at what is the effect of numerical aperture. You fix the value of A. Okay. And I always fix the value of this wavelength for now. And then see the effect of numerical aperture. And I see that if I reduce the numerical aperture, then there are less number of modes. Okay. So the number of modes decrease with core radius and numerical aperture. So this is about fiber parameters. What about wavelength? Would wavelength would wavelength have any bearing on the number of modes? For that, let us do an experiment. A very simple experiment. Okay. So what I do, I take a fiber with fixed N1, N2, and A, and then I use a laser beam whose wavelength I can vary. And I couple light into this optical fiber using some optics. MO stands for microscope objective. And then I image the pattern which is coming out of the fiber onto a CCD with the help of another objective. And so I capture it when it just comes out of the fiber. So this MO is very close to fiber, and so I prevent diffraction of this light, okay, so that whatever comes out, I directly image it. And then what I do, I change the wavelength and I look at the pattern, how the pattern is changing. All right. So this is the CCD output, and the wavelength is 200 nanometer. What I see this kind of pattern coming out of the fiber. When I analyze this, I find that this is the superposition of 39 modes of an optical fiber. 39 such patterns, which you see here. Okay. Now I increase the wavelength. 250 nanometer, 27 modes. 300 nanometer, 17 modes. The 350, 13 modes. 400, 10 modes. So I am increasing the wavelength, number of modes are going down. And you can see the green size here, the size of a speckle. This is known as a speckle pattern. The size of the speckles is increasing, okay, because the number of modes are increasing. If you look at the mode, then this is known as the fundamental mode. This mode would always be guided. Then this is first higher order mode. So you see the feature size here. As you go to higher order mode, the feature size is decreasing. Okay, and so when large number of modes are supported, feature size is small. And if you reduce the number of modes, the feature size increases. And if you go to 1500 nanometer, I see this beautiful pattern, which is just one mode, single mode. Okay, so you increase wavelength, you decrease the number of modes. So the number of modes depend on A, NA, and lambda. And fortunately, all the three parameters can be assimilated only in one parameter, which is known as V parameter, 2 pi over lambda naught times A into NA. Okay? And it so happens that if you do mathematical analysis, then you find out that if this parameter is less than a certain value, 2.4048, then fiber supports only one mode, and it is known as single mode fiber. Okay? This parameter is often known as normalized frequency because it has lambda naught in the denominator. Okay? Fine. So if V is less than this, then single mode fiber. V is much greater than this, multi-mode fiber. Intermediate value, now people have come up with new terminology, few mode fiber, because of new advancements in optical fiber communication. Okay? So single mode fiber is a single mode fiber which is packaged. This is a patch cord of single mode fiber. See, both the fibers, whether you are having single mode fiber or multi mode fiber, cladding size is the same, 125 micron. then you package it, and then you color code it. If it is yellow color coded, then it is single mode fiber at 1550 nanometer wavelength. Whenever I talk about single mode or multi mode, I will have to define a wavelength. Okay. So single mode optical fiber is used in long haul optical communication, has core diameter which is about 10 micrometer across. Okay, let me just come down to this. Typical parameters of a single mode optical fiber is relative index difference is 0.003, which corresponds to numerical aperture of 0.1, and A is 5 micrometer. Since it has very small core diameter, then coupling light into this is critical. Joining two fibers is also critical. So you require precision equipment and components. And that is why the components which are used in single mode optical fiber communication link, they are costly. Okay. On the other hand, if you have multi-mode fiber has a large core diameter. It supports large number of modes, 50 micrometer core diameter. Your delta is also quite large, so 0.01, numerical aperture is 0.2. All right, it is color coded as orange. Okay, so here, since the dimensions are large, so system equipments and components are less expensive. Do I have a little more time? Maybe I would need maybe 10 minutes more. Would it be fine?
Yes, sir, sure, sure.
Yeah. Okay. All right. So, now the question is, okay, we have understood optical fiber. Now, how data travels through optical fiber? How that binary data, sequence of zeros and ones, okay, which define our data, whether it is video, whether it is picture, whether it is voice, how it is carried through optical fiber. So it is carried in the form of optical pulse train. Okay, means laser light pulses. So you switch on laser, high pulse, this is 1. You switch off laser, low pulse, 0. So this is a sequence of zeros and ones. So you switch it on, switch it off, switch it on, switch it off, okay, like this. But not at this speed. It is at very, very high speed, okay. So this time is usually picoseconds, several picoseconds, right? So you send this optical pulse train through optical fiber, and when this pulse train travels through this, then we realize that these pulses do not retain their shape. These are temporal pulses. Okay, this is power as a function of intensity, power as a function of time. Okay, so these optical pulses become like this. So what happens is their amplitude goes down, their width increases. Okay, and this basically what would be the output pulses? It depends on the characteristics of optical fiber, which you will determine by the modes of optical fiber, and that is why the modal analysis of optical fiber is important. Okay. So now, what would be the bearing of this on our data rate or on our communication system? You can very well realize that if the amplitude goes down to a very low value, then your detector, because ultimately you will have to convert these pulses into electric pulses. So you have optical pulses, ones and zeros. You need to retrieve electric pulses, zeros and ones. And that is done by detector, which converts light signal into electric signal. And detector has a sensitivity. So if the sensitivity of the detector is certain sensitivity, and the amplitude of these pulses goes down below the sensitivity, then everywhere the detector will record 0. Ones would be missing and your data is lost. This is one thing. Okay, so this attenuation of the pulses should not be very large. So we should take care of that, the material of the fiber, that it should not cause too much losses to optical pulses. This is one thing. Second thing is, you see the broadening of pulses. Okay, if the broadening is too much, then these pulses will overlap. Okay, and then you don't know where the 0 is, where the 1 is. Then also the information is lost. Okay, so how much broadening would be there? It depends on the modes of optical fiber. Okay, that we will briefly look into. So you would not like that situation to come. Much before that situation comes, you take out the pulses from optical fiber, reshape the pulses, bring them back into original shape, and then send through another segment of optical fiber. And this bringing the pulses back into original shape is done in a device which is known as repeater. Okay. So what you should have a repeaterless length of the link, which should be as long as possible, because you would like to minimize the number of repeaters in a system. Repeaters are costly. Okay, they add to the cost of the system. So we have to take care of attenuation and broadening of pulses. Okay, attenuation. If you look at attenuation, it depends on the glass material, the material of the fiber, and optical communication grade fiber is glass. Okay? So the loss depends on wavelength, and we find that at 1550 nanometer wavelength, the loss is minimum for silica glass. So we use this wavelength, right? Nowadays we could, and if you look at other features, these are basically due to impurities. This is water peak and some other impurities. So nowadays we could make a fiber where all the impurities have been removed to great extent, and we have this kind of attenuation. But still, the minimum attenuation is about 1.19 dB per kilometer at 1550 nanometer wavelength. This is fine. One is futuristic system, that if we increase the wavelength from 1550 nanometer to 2 micrometer, then the Rayleigh scattering loss in optical fiber will come down. If you look at this trend is basically Rayleigh scattering, which goes as 1 over lambda to the power 4. So if you increase the wavelength, why there is Rayleigh scattering? Because when you make optical fiber, then wavelength scale inhomogeneities are frozen in optical fiber and they act as a scattering center. So there is Rayleigh scattering. So if you increase the wavelength to 2 micrometer, then Rayleigh scattering loss would be very, very, very small. But unfortunately, at this wavelength, uh, the absorption loss of glass is very large. Infrared absorption loss is very large, so we cannot use it. So you'll have to devise new material. Okay. For example, fluoride glasses, where the absorption loss is also very small at 2 micrometer wavelength. So people are working on this futuristic system where you can minimize Rayleigh scattering loss and minimize absorption loss also. But this is in research. Okay. Of course, you can amplify pulses, and you do amplify pulses with the help of what is known as erbium doped fiber amplifier. And so every 50 kilometers or 100 kilometers, you put one amplifier to amplify pulses, right? All right. So let me not go into. I have already explained this pulse broadening. Why there is a pulse broadening? Pulse broadening can be due to two reasons. One is intermodal dispersion, because there are several modes. If it is a multi-mode fiber, so there are several modes. Each mode travels with different velocity, and that causes broadening. This can be avoided by single mode fiber. That is why you use single mode fiber for long distance communication, because there is no intermodal dispersion. But still there is dispersion, and that dispersion is due to wavelength. Okay? You will say we are using single wavelength, then why there is a dispersion? We are using single wavelength source, laser source. We are using single wavelength laser source, but each laser source has certain line width. Okay, it is not strictly monochromatic. So even if it is a very small line width, so wavelength components which fall in that line width, they contribute. And the refractive index of the medium at those wavelengths is different. Also, the velocity of the mode, although it is only one mode, but at different wavelength, the velocity of the mode is different. So there is a dispersion. Okay, so we'll have to take care of that. For that, people design very exotic fibers to take care of that. And nowadays, people can do it by digital signal processing also, right? One very interesting thing, I have just 3 more slides. Okay, I'm winding up. So one very interesting thing that we can have here is that you have an optical fiber, okay, and you have a single wavelength which can carry data from one place to another place, okay, over several kilometers. All right. And if you want to do it over a very large distance, for example, 1200 kilometer, then you can use amplifiers in between. For example, in this link over which is 200 kilometer long, people have used 11 erbium doped fiber amplifiers. So about every 100 kilometers they have put one amplifier. Okay, but the interesting thing here is that in this fiber you can use several wavelengths at the same time. At the same time, several wavelengths can carry your data independently. For example, here we have used 10, these people have used 10 wavelengths, 10 different wavelengths, and each wavelength can carry data independently over 1200 kilometer. So the capacity of the fiber can be multiplied 10 times. So one wavelength can carry data at the rate of 10 Gbps, and if I am sending 10 such wavelengths, then it would be 100 Gbps. And people have now demonstrated several TBPS using this system. This is known as wavelength division multiplexing system, WDM system. Okay, fine. So now, what is the futuristic system where we are these days? Okay, where do we stand? If you look at the evolution of capacity, data carrying capacity of optical fiber over the years, then it has roughly followed this trend, which is defined, which is shown by blue line, which shows a trend that every 4 years the capacity of the optical fiber could be increased by 10-fold. Okay, 10 times every year. And we could keep up with this trend using various advancement in optical fiber communication technology, initially by improving the transmission, that is decreasing the loss, then by using amplifiers, then by using WDM system, then by using high spectral coding, how dense we can pack data into these optical pulses. But now we have reached the capacity limit of current technology, which is about 100 TBps, 10 to the power 14 bits per second. So the fiber which is now laid on seabed, which we are using commercially in commercial system, it has a capacity of this much. Okay, and we need this kind of capacity, right? Even more because now the bandwidth requirement is much larger, because now people are using no internet for everything, for television, for online talks, for online sharing of information, several things. Okay, so what people are doing now, okay, what is the solution to keep up with this trend now? Because we are anticipating, well, it is almost there, the capacity crunch. Okay, a possible solution is to use space division multiplexing. Wavelength division multiplexing we have exhausted. Now, what is the space division multiplexing? In space division multiplexing, what people are proposing, they have no, this is in research areas. People have already demonstrated several systems using this. So one system is that in one particular fiber itself, in the same cladding, you can have multiple cores, and each core can carry data independently. So you can multiply the capacity of fiber several times. This is known as multi-core fiber. I will not talk about this. Then there is another very interesting possibility where you use few mode fiber. So in the fiber, now you don't use single mode fiber, you use few mode fiber, where let us say some of the modes are traveling and each mode can carry data independently because they are orthogonal. Okay, what you will have to, you will say that earlier you said that you use single mode fiber, now few mode fiber. Yes, I have said that. Okay, when you use the current technology, when you couple light from pulses into optical fiber, and if it is multi-mode fiber, then light gets coupled into all the modes simultaneously, and that is why there is broadening of pulse. But when you use few mode fiber for communication, now what you do, you have pulses coming out from different sources, so from different channels which you want to communicate. So from one source you couple light selectively to one mode, from another source selectively to another mode, for yet another source selectively to another mode. Okay, so you avoid cross coupling of these pulses into modes. Okay, And since these modes are orthogonal, so if there are not so many perturbation in the fiber, if the fiber is carefully designed, then these modes can carry data independently. Okay, then this is a few mode fiber. So people are looking into it. Okay, so this is what which is coming up, right? Then you have some other exotic fibers also in the because we don't have much time, so I'm not able to touch upon that. And there are several things. Okay, I tried to summarize so many things in just 1.5 hour uh, lecture. And if you want to further look into it, then full course on fiber optics is available on YouTube. Okay, there is 40 lectures of half an hour each. You can go through that. Okay, thank you very much. I would be very happy to take up the questions.
Thank you so much, sir, for this amazing talk. Now it's time to proceed to our interactive Q&A session. I'll take out the name of the participants who have questions. In the meantime, others can also put their questions in the chat box. First, we have Preetham Singh. Would you like to unmute yourself and ask your question?
Hello, good evening, sir. My query is related to total internal reflection. The very famous phenomenon that we see around us related to TIR is mirage. That is that happens due to the change in density of air when we go from up to down the altitude. As that change in density is continuous, and there must be a point at which the angle of incidence of light is exactly equal to the critical angle. So the refracted light should go coinciding with the interface of air. So that refracted light should go uh, at the same angle. So as we have studied in the concept of mirage, that this should not happen. So how can we understand that?
Yes, so you see that you mean to say when it becomes exactly equal to critical angle, all right, then there would be grazing incidence. Fine. So in grazing incidence, you must say that it will go along the interface. That's what you are saying. But it comes back. So in mirage it goes like this, and then it comes back like this. All right. You can also have it, parabolic index medium, where where you have high refractive index here, and then if you go away, let us say this is the axis, this is the line where you have high refractive index, and then the refractive index decreases if you go away from this axis, right, in a parabolic fashion. Okay, now what happens is that if you exactly solve the equation, even if you don't solve the equation, if you just divide it into several layers, okay, of, let us say, constant refractive indices, and then you just trace the path of the ray, then it will go and come back, it would be having a sinusoidal path. You see, at the interface where you have grazing incidence, what happens is that this grazing incidence you cannot achieve practically in perfect way. Okay, because of the inhomogeneities, because whatever medium you take, okay, there would be certain amount of inhomogeneity, and because of that inhomogeneity it will always either get refracted or come back. Okay, so certain part may get refracted, certain part may come back. So the ray path would be something like this. Okay, in a parabolic index medium the ray path is sinusoidal. Okay, could I answer your question?
Okay, thank you, sir.
And next, we have Suhas Adiga. Would you like to unmute yourself? Okay, I'll read out the question. He's asking what makes optical fiber structure so special to have the least heat minimalization.
All right. So you see, you have an optical fiber. All right. What is heat basically? Heat is an electromagnetic wave itself, and that is infrared, right? Infrared rays are having wavelength much larger than the wavelength of light. Okay, if I compare visible light, okay, or near infrared, the you will say that for communication also I am using 1550. Okay, 1550 is near infrared, but it is not heat wave. Okay, it is not heat. Heat is much longer, right? So what happens in an optical fiber? The longer wavelengths are not supported. Okay, for longer wavelengths, most of the power is in the cladding. Okay, as you decrease the wavelength, then more and more light in the core. As you increase the wavelength, light will spread out in the cladding and it will radiate out. Okay, so 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 your heat, that is infrared, that is not guided that much as the other wavelength which is of interest, or visible light. Okay, and also uh, this is optical fiber. It is a cylindrical structure, so it has got very large surface to volume ratio. So heat dissipation is also very quick, okay, because you have very large surface area. Particularly, it is useful in making optical fiber lasers. Okay, in optical fiber lasers, what you have is you have two advantages. One is your gain medium is very large. In a laser, what do you have in a laser? You have a gain medium, you pump it. Okay, you pump a gain medium, and then you have a resonator. Okay, then it will go back and forth and lasing starts. Okay, now in optical fibers, you have possibility of very long gain medium. You can have 20-meter long fiber, 20-meter long cavity, which you cannot have in a normal laser. Okay, you cannot have helium neon laser with 20-meter long cavity. Okay, but in optical fiber you can have. So this is one thing. Second thing is that you can make very high power lasers because the fiber structure is such that it very quickly dissipates heat. Okay.
I hope your question was answered. Now we have Khushi Lalit. Would you like to unmute yourself?
Good evening, sir. My question is, what kind of damages can occur to fiber cables under the ocean, like earthquakes or
Yes.
ocean wildlife may interact?
Yes, this happens. This happens. Sometimes what happens is, although people mark it very clearly and see that at these places optical fiber cable is there, but sometimes what happens is that ship rams into it and it damages optical fiber. Okay, then people have to correct it. Okay, and during that time internet traffic stops. Okay, people take care, but these accidents do happen, but this can be corrected. Okay, so when an optical fiber is broken. Okay, so you see, when you have your copper wire communication, a copper wire is broken, you just join it and twist it and it starts working, okay, very quickly, right? But in optical fiber you cannot do this, right? So it has advantage also and little disadvantage. Advantage in the sense that if you have copper wire line, then anybody can eavesdrop and can listen to the conversation. Okay, just join his headphone there, handset there in the copper wire and can listen. But in optical fiber it is not possible. It is glass fiber. When it is broken, then the disadvantage is that it has to be joined with the help of very specialized equipment, which is known as a splicing machine. Okay, splicer. So what happens is that if you have a broken fiber, in that machine you put that fiber, right? Both the ends of the fiber. First, you have to cleave the ends of the optical fiber very nicely, okay, with mirror finish and very straight, and then you put them together in the machine. That machine aligns these two fibers. There is a microprocessor there. The machine images it, okay, and there is a microprocessor. So by aligning the images and doing corrections, it does align very precisely. and then these two fibers come very close to each other. Then there are two electrodes, and between these two electrodes an arc is produced, electric arc, and with the help of that arc the glass is melted and these two fibers are fused together, okay, and they can be joined. Okay, this can be taken care of. Okay.
Yes, sir. Thank you. And my next question is optical fiber communication hackable?
Sorry, is optical fiber communication hackable? Uh,
Hackable. Yes.
yeah, can you hack it? Well, you see, as I've said that if you compare it with no telephone line communication, it is much secure. If you compare it with microwave communication, it is quite secure because in microwave also you can tap it because it is open communication. But still there is a possibility that people can hack. Okay, people can hack any data from anywhere now. No, so maybe at the repeater site or maybe at another site where the data is being downloaded. Okay, so now that is why these days there is emphasis on quantum communication. Now people are looking at quantum communication where it is completely hack proof. Okay, so people are looking at optical fiber communication using quantum. Okay, this will require maybe another lecture if I try to explain, but there is a possibility of hacking it, and that is why people are working with, particularly with the advancement of now quantum computing. People are now developing quantum computers. With the help of quantum computers, anything can be hacked very easily, and that is why now people are developing quantum communication, which is hack proof. Okay, the work is going on. In China, they have demonstrated from Beijing to Shanghai this secure quantum communication over, I think, 4,000 kilometer distance or 2,000 perhaps. Okay, using uh, Earth to satellite and optical fiber links. Okay.
Yes, sir. I got it. And sir, one more question. What are the primary materials used in making fibers and the effect of this industry on environment?
Effect on, sorry, say that again.
The effect of fiber optics industry on environment, like the making process of it.
All right. I don't think it adds to pollution. Okay. So what happens is that how the fiber is made basically. We have to understand that. You see, when Charles Cow was working on the fiber, then the fiber was being made using existing glass. Okay, and we want to have very 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 pure glass so that the losses are very small. So you start with chemicals. Basically you basically create glass, make glass itself in the laboratory. Okay, so for example you use you use SiCl4 and you oxidize it, okay, in oxygen environment, and then you produce SiO2, silica, right? So this is done in very controlled environment, so no fumes are emitted there, which is done on glass working lathe. So you made a very thick version of optical fiber, very short and thick version of optical fiber, which is known as preform, and then you take that preform to a tower, okay, which is 3 story high, which is as high as three story building, and on top of the building there is a furnace. You melt that there, and then when it drops, okay, then you take the fiber out of it and then you wind it on a drum. So this is very sophisticated and very expensive process in controlled environment. There is not much impact on climate, I suppose. and this is glass, so glass does not pollute environment.
Okay, sir. Thank you so much, sir, for answering.
Okay, now we have Jaspreet Kaur. Would you like to unmute yourself?
Hello, sir. So my question was that if I stay close to optical fibers for long period of time, does it affect my health in any way?
I'm sorry, your voice is breaking.
Am I audible, sir?
Yes.
So my question was that if I stay close to the optical fibers for a long period of time, does it affect my
If you
health
take,
in any
sorry,
way?
sorry, again the voice is breaking. If you take,
I'll read out the question.
yeah.
She's asking, if I stay close to optical fibers for long period of time, does it affect my health in any way?
No, 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 because it is made of glass. Okay, it is made of glass, and you see, this fiber is usually either buried underground or buried on seabed. Okay, so there is a very little chance that you will be in contact with optical fiber for a long time. Okay, it would be just like, okay, glass itself would not make any impact on your health, but whatever is outside, you have packaging, you have plastic, okay, packaging there, just like you have your electricity wires. Okay, so it is like that. And in electricity wire, you have electricity coming out. In mobile phone, you have microwaves which are coming out. But optical waves are very safe. Light is safe. Okay, you have sunlight which has entire spectrum, and it is safe for you, right, except UV, of course. Okay, and the power levels which these optical pulses carry are very, very small. Okay, so it is quite safe.
Thank you. Now we have Sarthak Jain. Would you like to unmute yourself? Okay. So he's asking, what is the future trend expected in this as Starlink is getting popular these days?
Yes, Starlink is getting popular, so you can have communication using satellite, and when you have communication using satellite, then it is line of sight communication. Okay, and moreover, so either you have line of sight communication using optical waves, or you have using microwaves. Microwaves have their limitations. Okay, microwaves have their limitations, but in terms of data rate, so till now we do not have any other system which can give you much better data rate compared to optical fiber network. Okay, but people are looking at free space optical communication also. Okay, and a combination of optical fiber communication and free space communication, right? These people are looking at, but how things will take shape, I cannot tell. But it is my guess that optical fiber communication is going to stay, and it has to stay. Okay, you cannot replace it with any other communication system, at least in near future. I don't see. Maybe partially, to some extent, partially you can use those systems, but fully replacing the system is not possible in near future.
Okay, so we have a question from YouTube as well. Devanshu is asking, what if the pattern was not related to Rayleigh scattering?
What if the,
Pattern was not related to Rayling's scattering.
sorry, I could not still get, which is not related to Rayleigh scattering?
The pattern is written pattern.
Pattern.
Yes.
No, it has nothing to do with pattern. Any pattern you have, okay, any pattern you have, any light you have, if the size of the inhomogeneity is of the order of wavelength, then there is Rayleigh scattering. If the size of inhomogeneity is much smaller than wavelength, then we call it my scattering or me scattering. Okay, scattering would be there if there is inhomogeneity in the medium. Scattering has to be there. It has nothing to do with pattern. For every pattern, for every mode, there would be scattering. Okay.
Okay.
Thank you,
So
sir.
now we have last question from Samarth Jain. Would you like to unmute yourself? Okay. So he has 2 or 3 questions. First, is there any work? I'm audible?
Hello.
Yes, sir. I'm
Yeah.
audible. Yeah.
Yeah.
He's asking, is there any work being done in reducing the wires to even smaller levels like micro or nano optical wires?
These are already micro optical wires, I would say. Okay, because if you look at core dimensions, they are 10 micrometer across. Okay, cladding is 125 micrometer. So these are already micro wires, right? Uh, Nano wires, nano optical fibers are used, okay, for different applications, right? For example, for sensing, you can use it. For people are now making nano antennas for other purposes. For example, trapping of some particles, right? So so nano optical fibers, nanophotonics, it has also come up. People are working on this, but not for telecom purposes. Not for telecom purposes. For telecommunication purposes, this is the fiber, okay? And other fibers are being developed, which are few mode fiber. And nowadays, another thing is coming up, which is orbital angular momentum mode fiber, which I could not touch upon in this talk, okay? Which is very involved and very a bit difficult to understand. uh, but all these fibers, they have dimensions of the order of microns.
He has another question. Are there any possible application of optical fibers in nanotechnology apart from sensor development?
Okay, as I have said that you see, people are now doing near field optics using optical fibers. So where you use nano size optical fibers for trapping of data, people are using trapping of particles. Okay, because what happens is that if you have nano dimensions, then the field extends quite a lot, okay, outside the fiber, and there is a field gradient, okay. So modal field is there. Modal field means light amplitude, okay. So there is a gradient, okay, there. And whenever you have this field gradient, then you can have a force, okay. You can generate force of the order of, let us say, piconewton. And if you have nanoparticles, then those nanoparticles will experience that force, that gradient, and then they can get trapped. So people are working on that, okay.
He has one more question. During the discussion about chaos conclusion, a loss of 1000 dm per kilometer was mentioned. Were impurities in the fiber material solely responsible for all that loss in the optical fiber, or were there other factors as well?
So you see, so there are several kind of impurities. You have iron, chromium, okay, vanadium, okay, all sorts of impurities. And iron had lot of no contribution to the losses earlier, and then water, okay. Even the fiber that I showed for spectral variation of losses, so that has very high water peaks, okay. So water was also a very big contributor to these impurities. But now people have developed technologies to remove even water peaks. Okay, earlier even Corning has removed most of these impurities when they came up with a fiber of 16 dB per kilometer from 1000 dB per kilometer. They have removed most of the impurities, because they started with the chemicals, not with existing glass. They started with chemicals itself to make glass. Okay, but still moisture was there, water peaks were there. So nowadays people have developed technology with which even water peaks have been removed.
Okay,
Thank you, sir. Thank you, Jasmeet.
you're welcome. Now, I think that was all the questions we have. With this, the Q&A session has come to an end. I hope everyone's queries has been answered. Now, can I please request Nimi ma'am to speak a few words?
Yeah, good evening, sir.
Good
Actually, I
evening.
just want to, yeah, I just want to thank you from my heart for accepting this invitation and encouraging our students. And I'm really sure that my students must have gained a lot of knowledge about optical fibers, including myself. Although, due to some reasons, I joined 10 minutes late, but it was a very encouraging and a very enlightening session. In fact, I have also come to know certain things about optical fibers, although it is not my field, but it seems to be an interesting field now for me also.
Thank you.
And I'm really thankful to the students and to the teachers also who have been a part of organizing this event. And again, thank you very much for your support, sir.
Thank
Okay,
you.
sir.
Thank you very much. Okay. So can I log out now?
Yes, sir, just a few minutes. Now, we will just take a screenshot. Everyone can turn on their cameras, and we would again like to thank you for being with here with us today. We hope to see you again in the near future. We also thank all of our guests for their time and patience. Hopefully, you all enjoyed the session. Meanwhile, you guys are turning on your cameras. If anyone has any suggestions, then please fill out the feedback form posted in the chat box. Here is our Linktree link. You'll find our website link as well as all our social media's handles. Stay connected with us on the social media to get updates on the future events. Is the screenshot done? Okay. So, thank you so much, sir. Again, you can all be.
Yeah. Thank you. Thank you so much.
Thank you, sir.